CS08-Coin-Flip. This is the Jupyter Notebook Coin-Flip, a probabilistic bit by Abuzer Yakir Yilmaz that I have placed on Google Colab. This describes the probability of flipping coins that are either fair coins or biased coins. First, let's discuss the concept of a fair coin. A coin naturally has two sides, heads and tails. After flipping a coin, we get either heads or tails, which we can represent with 0 or 1, respectively. If our coin is fair, then the probabilities of getting heads and tails are equal. The probability equals 1/2 or 50%. Flipping a fair coin can be represented as an operator. If you have a fair coin function or operator and your last flip was heads, on the next flip you still have an equal probability of getting either heads or tails on the next flip. And likewise, if your last flip was tails, a coin has no memory. Now, if we represent it as a table, the initial states are shown in the row at the top, and the final state is shown on the column on the left, and we clearly see that all probabilities are 50% or 1/2. We can also represent this table using 0 and 1. The probabilities remain 50%. Now, for task 1, let's simulate a fair coin in Python. Let's flip a fair coin 100 times, calculate the total number of heads and tails, and then check the ratio of the number of heads and the number of tails. Then let's do the same experiment 1,000 times. Then do the same experiment 10,000 times. Then do the same experiment 100,000 times. Do our results get close to the ideal case where the number of heads and tails are equal? Let's peek at the solution. Here we see in the solutions this code where we select the rand range method from the code library random. Then we run a for loop where we iterate through a list containing our experiment amounts of 100, 1,000, 10,000, and 100,000. We initialize the values of heads and tails to start at 0. Then we run another for loop for the range of our experiment, where we have a condition where the method of rand range is bounded by n-1, so we put 2 there to indicate we only want values of 0 or 1. In the condition where the result is exactly 0, then the heads counter is incremented by 1. Else, tails is incremented by 1. Then we print the number of trials in our experiment. Then we print the number heads and tails. Then we print the ratio of the number of heads to the number of tails. Then we print a blank line. We do this for each element of the list experiment. Throughout these outputs, what we are looking for is the ideal ratio of 1. So let's run it a couple times to see that how far are we from 1. This is below 1, above 1. And then also, when we run it 100 times, is that more accurate than when we run it 100,000 times? No, our accuracy improves on our probability the more often we run the program. If we run it only 100 times, it's not quite as valid as when we run it 100,000 times. We're more likely to get the number 1 or get close to the number 1. But not each time, because there is an element of randomness here. Now let's look at flipping a biased coin. Our coin may have a bias. For example, the probability of getting heads is 60%, which is greater than the probability of getting tails, which is 40%, regardless of the previous flip. In this case, the ratio of heads to tails will change from 1.0 to 1.5. Let's peek at the solution to see how to do this. In this code, we select the rand range method from the code library random. Then we run a for loop where we iterate through a list containing our experiment amounts of 100, 1,000, 10,000, and 100,000. We initialize the values of heads and tails to start at 0. In the second conditional statement, the second for loop, we go from I, 0, to the number of trials for this experiment, 100, 1,000, etc. Rand range picks a number from 0 to n-1, which in this case is 99. Then that number is compared to 60. If it is less than 60, then the heads counter will be incremented, else the tails counter will be incremented. Next, we print the results as before, and we look for a resulting ratio of 1.5, and we will see how close we get to it. Let's run it a few times to show it working. This is a simulation of a bias. As no real bias is introduced other than that contained in the function rand range. It's a simulation, but a very realistic one. Oh, look, we got very close to 1.5. That would be the ideal. Now let's program a biased coin using mathematical precision. First, we pick a range for the precision of probabilities, say n, as n equal 11, 101, 1001, or 10 to the power of k plus 1 for some k is greater than 3. Next, we pick the bias, say b, as an integer in the range 0 to n. We fix n and b as definite integer values. Third, we pick a random integer in the range 0 to n-1. If this random integer is less than b, we output the string heads. Otherwise, we output the string tails. In this way, we have a biased coin landing on heads with probability b over n, including 0 and 1. Note that we pick n equals 10 to the power of k plus 1 as an odd number. In this way, the coin cannot be fair as long as b is an integer, because the half of an odd integer is not an integer, it is a float. Task 3. Let's write a function to implement the described biased coin. The inputs are integers n greater than 0, and b is an element of the set which ranges from 0 to n. The output is either heads or tails. Let's peek at the solution. Let's explain the solution for task 3. DEF is the reserve word for defining a function, and this function is named biased underscore coin, which takes two inputs, n and b. And again, we import rand range from the library random and use it to choose a random number from 0 to n-1. We then compare this number to b. If the number is less than b, then we return the string heads. Otherwise, we return the string tails. There is no output to this code cell, as it is a function definition, which will return no output unless called by another cell. Now let's discuss task 4. Using the function defined in task 3, we run a series of trials as we did in tasks 1 and 2. We pick n as 101. Our task is to determine the value of b experimentally without checking its value directly. Flip the same bias coin 500 times, collect the statistics, and then guess the bias. Compare your guess with the actual bias by calculating the relative error in percentage, the absolute value of the difference divided by the real bias. Let's peek at the solution. The first code block is our function from task 3. The second block fixes n and b as our integer values. The third block runs 500 trials of a coin toss as follows. First, we initialize the number of total tosses to 500 and initialize the counter of heads to 0. Then we set up a for loop to run from I, 0, to the number of total tosses minus 1. And then for each iteration of the loop, we have a conditional statement which checks to see if the bias coin function returns the string exactly heads. If so, it increments the number of heads counted. The next block of code sets my guess to the number of heads divided by the total tosses. The next line calculates the real bias as B divided by N. The line after that calculates the error as the absolute value of the ratio of the quantity of my guess minus real bias to the real bias multiplied by 100. The final block of code prints the results. Boy, that's a big error. Let me try that again. That's a lower error. So we have fun with this. It's very random, and we're getting a good answer with our bias coin.